All right, so today what we're going to do is we're going to start getting into the different types of tests we can do. So we looked at a geometric series, right? We looked at a telescoping series. But for series that are neither of those two things, we're going to have multiple tests that we can apply to see whether a series converges or diverges. And you're going to see that all the different tests we're going to use, that there are kind of like tells in the function that kind of tell you when that test might apply and when not. So today we're going to talk about the integral test, right? And so this is when section 8.7 kind of comes back up. So back at the end of the last unit, we started talking about improper integrals. And when we talked about improper integrals, we saw what we were really doing is we were learning how to integrate around an asymptote. So when we looked at a integral to infinity, those were usually horizontal asymptotes, and we were trying to grab as much area of the tail as we could. And then if we had an integral with bounds that were non-infinity, right, they were finite bounds, well, if there was an issue with one of the bounds, we usually saw that that correlated to like a vertical asymptote. We were trying to grab the area in that tail. So the integral test, right, there are some conditions that must be true about the sequence in order for it to apply. So first of all, your function has to be positive, it has to be continuous, and it has to be decreasing for all x greater than or equal to 1. And when you know that you can apply this is when the series that you're looking at, when the equation of the series looks like a function that we could graph that would fit this criteria. So a sub n, which would be the nth term of your series, can be rewritten as a function of n where these conditions are true. So then what we say is that the series and the integral, so, and one thing I want to make sure that we see about this definition right here, we kind of default to 1 when we're writing a general series, right? But we know that this index can start anywhere we want it to. For the integral test, it really does need to start at 1, okay? But it could also start bigger than 1. So we could start at 2, we could start at 3. The bounds on the series must match the bounds of the integral. So if we start the series at 2, then we would start the integral at 2. So what we're saying here when we apply the integral test is that rather than using a traditional limit to determine if the series converges, we're going to integrate the function, and the integral and the series will behave the same way. So the series and the integral will either both diverge or both converge. So one of the kind of big kind of clues when you want to use the integral test is a lot of times if you see natural log in your series anywhere, you should just take a second and go, oh, could I integrate this? Okay. So sometimes we can actually just take the limit and be done, right? If the nth limit is non-zero, then we know it diverges. We can just stop right there. But sometimes if the nth limit is 0 and you still don't know if it converges or not, kind of check and be like, ooh, could I integrate this with a u substitution, right? So natural log's a big clue. Also, any kind of function where it's a recognizable f of x function. So let's actually look at an example. So let's say we have the series from 1 to infinity of n over n squared plus 1. So if I was looking at this, right, I could do the nth limit and that would go to 0, right? But that's not going to tell me if it converges or diverges. That just tells me I've got a shot at convergence, right? It's not a geometric series and it's not a telescoping series. So we don't really know how to find convergence outside of those yet. But if you look at this and you look at that denominator, well, 99 times out of 100, right, we're going to want that denominator to be our u if we want to u sub this. So the derivative of the denominator would be 2n. Well, I do in fact have an n in the numerator that I could create 2n out of. So this would actually be a function we could integrate, and we would say, well, first let's check the infinite limit, because if this is non-zero, then we're done, right? This is obviously is 0 because the power in the denominator is higher than the power in the numerator, right? So let's let f of x be x over x squared plus 1. And this is continuous. It's positive for all values greater than 1. And we can see, because the infinite limit is 0, right, it is going to decrease and go towards 0 over time. So it fits the conditions for the integral test. So if we integrate this function from 1 to infinity, well, we can see, we already mentioned we can do this with a u substitution. So I'm going to let u be x squared plus 1. That means my du is 2x dx. And then remember, we always want to go back to the function and find the elements of this that are already there. So I have the x and I have the dx, so you want to solve this equation for what you have. So I'm going to replace x dx with du over 2. So when we do improper integrals, right, we obviously can't integrate to infinity directly. So what we do is, and when we're making a u substitution, this is one of the main situations where we don't want to change the bounds on a definite integral to u. We just want to turn it into an indefinite integral, finish the integral, and then we'll deal with the bounds on the back end. So this, when I translate this back over to my variable u, I'm just going to leave it as an indefinite integral. We'll worry about the bounds at the end. And I'm going to replace the denominator with u, and the numerator, right, is just going to be 1, and I'm going to factor the 1/2 out front. So if you check this, there's my du over 2, and there's my u, and the x got eaten up in the du. So that's, everything's where it should be. So this is a pretty straightforward integral. The antiderivative of 1 over u is the natural log of u. Okay, so this was an indefinite integral, so I had my constant integration. Now I need to go back to variable x because that's what we were measuring. So u was x squared plus 1. And I need to evaluate this from 1. Don't put infinity here. Remember, we just name it another letter. And usually we name the guy at the top b and we name the guy at the bottom a if needed, because we always integrate from a to b. Okay? So here's our bounds, and we'll say, well, this is 1/2 the natural log of b squared plus 1 minus 1/2 the natural log of 2. So the next thing that we do is we say, well, we need to see what's happening. Yep, sorry, question? Does the c fall off? Okay, yes, the c falls off because here it was indefinite, but when I got to here, I put the bounds back in, so I don't need the c anymore. Yep. Question?
But we're on that step right there, could we just put bounds on it?
Like when you're here?
Like right before that, can we put bounds
Here?
Yes.
No, because you changed variables. And so remember, this is saying x equals 1, x is infinity, so when you change to u, they would have completely different bounds. So that's why I said this is the one time where I would not recommend changing the indices. But remember, when you're doing integrals, that's telling you what the variable is, and it is implied that there is a, whatever this letter is, that it is that equals that, that equals that. So that's why people go crazy when you don't do that, because it's a completely wrong thing, okay? It'd be like, it's literally like translating into another language and then leaving half your sentence in English, right? It doesn't work. So when we get to here, right, we need to see what happens as b goes to infinity, and we check that by taking the limit, right? Now I'm going to be able to drop the absolute value signs when I take the limit, because we're going to positive infinity, and we know that this expression will always be positive, and that's okay in logs. So we're going to now take the limit as b approaches positive infinity of 1/2 the natural log of b squared plus 1 minus 1/2 the natural log of 2. So what's the limit of the natural log of this as b goes to infinity? Think about what the graph in natural log looks like. It's infinity, right? So natural log of x, right? Looks like that. So as the values inside the log get bigger, it is going to infinity. It's just going to infinity very slowly, but it is going to infinity. So this equals infinity. So what this means is when we integrated this function, it means the area under the function was infinite, okay? So remember, infinity is, when it comes out as limit, is it does not exist. So we would say that the integral diverges, and according to the integral test, that means the series also diverges. So the integral and the series will behave the same way. So what do we look for? All right. Well, we need the nth term goes to 0, right? And we just test that by taking the infinite limit of the nth term. And so remember, what this means is that it might converge. If that limit is non-zero, definitely diverges and you're done. Also, we want to look for expressions that makes sense as a continuous function of x. So a factorial, for example, would not be a candidate for this, right? -1 to the n in there, if it's alternating back and forth, would not be a good candidate to this, right? So it has to be something we could draw as a nice fluid function of x. And when you're practicing and doing problems, a really, really great graphing utility that you can get online, there's even an app for your phone, is, some of you probably saw this in high school, but Desmos. It's really great. It only makes graphs. It's really pretty. It's really clean. But if you ever just want to throw it in there and see what it looks like, you know, and that'll kind of give you an idea. And I actually recommend looking at these things, because the more you look at these functions, the more you'll be able to visualize them when you're doing them on your own. Okay. So does anybody remember what we said when we did the integral test, or sorry, not the integral test, when we did improper integrals, what we were kind of saying conceptually about what happens when it diverges versus converges? I actually had a question on the test about that, right? We did the improper integral and I was like, what does this mean? All right. So you're trying to capture the area under the curve, right? And we have a tail, right? And that tail's definitely going to 0. If the tail is too fat, right, then by the time those terms get to 0, we've already grabbed infinity, so it's too late. Even though you're adding zeros, you're just adding 0 to infinity. But if the function drops to 0 very quickly, the tail is very thin, and so by the time we get to the 0 terms, we've already captured finite area, okay? So that's sort of the same concept with series, right? Because an integral is summing, and a series is summing. So if the faster something gets to 0, the better shot you have that it's going to actually converge, because we're just going to be adding 0, 0, 0, 0 at the end, right? So let's look at the next example I have. Now, pay attention to this guy right here, because the next one I'm going to show you looks very similar to that, but you'll see the next one's actually going to have a better shot at convergence. So this looks very similar. It's the same denominator, but the numerator is only 1 instead of n. So that n in the numerator on the last function was, even though the denominator is going to 0 pretty fast, that n on the numerator was slowing it down because it was making the fraction bigger, right? Because we still had to plug something in. But now that the numerator is only 1 and the denominator is dropping very quickly, this thing's actually going to get to 0 much faster than the previous one we looked at. So when we did improper integrals, the 2 examples that I showed you of this was we looked at 1 over x, which definitely goes to 0, but we saw that that diverged. But when we looked at 1 over x squared, it converged because 1 over x squared got to 0 much quicker than 1 over x did because we were squaring the terms in the denominator. And then we said, well, then 1 over x cubed, 1 over x to the 4th. We saw that the faster that denominator gets to 0, the better shot at convergence you have. Oops. So this is definitely something we can integrate. This is actually a known derivative. What is it? What's the derivative of? Arctan, okay? So I can actually integrate this guy directly, so it's a perfect candidate for the integral test. Later we're going to see the same function again, and we see that we can do it another way. So it definitely fits all of our conditions. It's positive, it's decreasing, it's continuous, right? So when we integrate this, we can do it directly, and we can say, well, this is just arctan of x, and we're going to evaluate it from 1 to b. And so in order to evaluate this, just like before, we need to look at the limit of b as b goes to infinity. So what is arctan of b going to be as b goes to infinity? So let's look at the graph of arctan of x. So arctan of x is the inverse of tangent. So for tangent, right, we know it kind of looks like s's and they repeat again and again and again, but when we flip it over the line y equals x, it turns on its side. And when you take the inverse of a function, any vertical asymptotes it had become horizontal asymptotes. So right around 0, arctan has a vertical asymptote at pi over 2 and negative pi over 2. So that means its horizontal asymptotes are going to occur at y equals pi over 2 and y equals negative pi over 2. So as the values of x get bigger and bigger and bigger, the graph is approaching pi over 2. So that means the limit as b goes to infinity of arctan of b will simply be pi over 2. However, we have arctan of 1. Somebody remember what that is? Pi over 4. So remember with arctan, the point goes in, right, and the angle comes out. So if you've got arctan as 1, that means sine and cosine are the same, and they're the same at 45 degrees, or pi over 4. So pi over 2 minus pi over 4 is just pi over 4. So because we got an actual answer, right, this means both of these things converge. So do not fall into the trap that the series converges to pi over 4, or that the series sums to pi over 4. That's not what we're saying. We're just saying that the series sums to something, okay? So why is this working for us? So let's go back for a second and look at what integrals actually do for us, all right? So I'm going to graph the original function, 1 over n squared plus 1. And it looks like this. So when you first learned to integrate, right, what we did is we took the area under the curve and we broke it up into rectangles. Right, so I'm just going to look at, we're going to let our delta x be 1, right? We're just going to have rectangles of width 1. So we break it into rectangles, and we would either use the left-hand sum or the right-hand sum. And so if we did the left-hand sum, we would start on the left, right? Draw a rectangle of width 1, come back down, right? Draw a rectangle of width 1, width 1, with 1. So you could see here for a decreasing function, the left-hand sum, if you summed up all the areas of those rectangles, you were overestimating the area because you were getting more than was actually there. But then we learn, right, well, you can also look at the left-hand sum. So if you did the left-hand sum, right, you would go up and draw your rectangles from the left side of those points. And you could see that that area underestimates the area of the curve. And so we knew that the true area was somewhere in between those values, right? What the series does is the series just says evaluated at 1, evaluated at 2, evaluated at 3, evaluated at 4. So the heights of these lines, let's see if I can find another good color here. If you evaluated at 1, the answer is just that distance right there. If you evaluated at 2, you're getting that distance, this distance, this distance, and this distance. So if you add up those lengths, it's going to be less than the area of the rectangles that we get, okay? So what we've now decided here because it sort of like sucks because when we first show you series, we show you series where we get a nice answer. And then I said, you're going to start getting to a point where you can't really get the answer. You just know the answer exists. I mean, we could do some fancy, sophisticated math and maybe get there, but that's beyond this class. But can we find the sum? So if we let delta x be 1, and we look at the area under the curve, we see that the left-hand sum is summing 1/2, right, 1/5, 1/10. And all I'm doing there is adding up the heights of those rectangles. So the reason I don't have to put the width of the rectangles, the width is just 1. So it's 1/2 times 1. It's 1/5 times 1, right? The right-hand sum is essentially summing up the values 1/5, 1/10, 1/17. So the area that we got of pi over 4, which is actually the true area because we used an integral to get it, is always between, in this case, our left-hand sum and our right-hand sum, because the left-hand sum overestimated, the right-hand sum gave us an underestimate of the area. But if you actually look at this particular series, if we go back to the series we were evaluating and we start at 1, what's the first term? So if you plug 1, what's the first term? 1/2. What's the second term? 1/5, right? So if you look down here, on this one we got lucky, 1/2, 1/5, 1/10. So the left-hand sum of this integral, if you let the width be 1, is actually the sum of the series. But to get that true answer, you'd have to do it all the way out to infinity. So pi over 4 is actually less than or equal to the sum of the series, but we know that the sum of the series is finite. So even though the sum is probably going to be maybe a little bit bigger than pi over 4, it's slightly bigger or equal to, okay? So this is why this test actually works for us, okay? And we can say, well, the behavior of the integral is going to match the behavior of the series. So all you're going to be able to do with these is say it converges. But if you get an answer, don't say the sum is pi over 4, because it's not pi over 4. Okay, it's just somewhere near there. So now we have another series that we actually recognize. So a P series and a harmonic series. So a P series has the form of 1 to infinity of 1 over n raised to the p. P is a constant number, okay? N is the variable, so it'll be like p squared, right? P cubed. So if you expand this series out, n is the variable that changes, p stays the same. So if we look at the first couple of terms, you would have 1 over 1 to the p, 1 over 2 to the p, right? 1 over 3 to the p. And what we'll see in a second, I'll show you why, but if that value p is greater than 1, the series converges. If the value of p equals 1, well then the series is just 1 over n. And that is 1, right? Plus 1/2, plus 1/3. And so when p equals 1, it has a special name, and we call it the harmonic series. And the harmonic series diverges. So we prove, right, this idea using the integral test, because these are all going to be integrable functions, right? 1 over n to the p, you can just move that into the numerator and you simply use the power rule to anti-differentiate, okay? So I'm going to show you why this is true for these values of p, because this is a huge important idea, because if you ever recognize a p series and we can hide them in plain sight from you, it's a snap to tell if it converges or diverges. So you really need to understand where it comes from. I'm going to show you the general proof. I am not going to expect you to regurgitate the general proof. However, on the exam, I may give you a p series and I may say, prove to me that this p prove to me that this p series converges or diverges, but I will give you an actual constant p to use. So I might say like 1 over n to the 4th, right? So what you're supposed to know is that you prove convergence or divergence with a p series by using the integral test. So you would just do the integral test on the series I gave you and show me whether it converges or diverges. But I'm not going to give you just a random p. I'm going to actually give you a number. Yeah.
For the p series test to work, if you use the previous example of like n over n squared plus 1, would you apply to that as well too? Maybe be your denominator exponent, or would you still?
Yeah, so you're going to see that there's a test coming up down the road that we're going to look at where, yes, the first 2 examples I showed you were examples of p series. The first one with the n in the numerator and the n squared in the denominator is just a manipulation of 1 over n, because that's what the power is reduced to. Like if you were taking the infinite limit of that, you would have said, oh, well, I have a 1 in the numerator, I have a 2 in the denominator, it goes to 0, right? Well, really what we were saying is it reduced to 1 over n. The second one I gave you had a 1 in the numerator and n squared in the denominator, and really that was just a form of 1 over n squared. So a little bit, about another section or 2 coming up, I'm actually going to show you how to go, yeah, that's a p series, and how you can show very quickly that it is a p series and do the limit. There's just a different technique for that.
Real quick, so what instance would it be where the p series would not work? You have to look at the given function.
If you had something other than like constants or polynomials in there, so if we had a cosine, or we had a sine, or we had like some natural logs or something in there, then that wouldn't really fit the criteria for p series. But if you have a polynomial over a polynomial, right? We saw it on the quiz on Tuesday. I gave you one and I said, a lot of people are like, oh, do I use L'Hopital for this? I was like, well, you could, but you'd have to do the derivative multiple times to get down to a constant, right? Or you could say, well, this limit is just equal to the ratio of the highest power in the numerator the highest power in the denominator, and when the ends canceled, it reduced it down to its p-series. Okay, so yeah, that's coming up, and we're going to see that we can do this other ways. So just keep in mind that, like I said, if I ask you on the test how to prove or show me, right, because we already know it converges, you can cite it on any other problem, but if I actually say, show me that this p-series converges, you prove a p-series converges by the integral test, okay? And they're very easy to integrate, right? But let's see why this is true. And I like this proof because it's very intuitive and it's something you guys can easily understand because we know how to do all this stuff. All right, so if we have 1 over p, or 1 over n to the p, sorry, we can easily compare that to the function 1 over x to the p, right? And we know that this is continuous and decreasing for x is greater than or equal to 1. And so we can apply the integral test as long as p is a value greater than 0. Right? If p is 0, well then n to the 0 is just 1, and that's a divergent series. That's just the constant series 1, okay? So p has to be some actual number greater than 1, or really it has to be non-zero, because I'm going to show you when we get done with the limit that there is a way to deal with values between 0 and 1, okay? But it's still got to be greater than 0. It's still got to be positive, all right? If p were negative, if I had n to the negative 2, what would happen to that? It would move to the numerator and become n squared, and that would diverge, right? So that's why you got to have a positive exponent in the denominator. All right, so let's look at this. So we're going to apply the integral test from 1 to infinity of 1 over x to the p dx. And just to make the integration a little easier, I'm going to rewrite this as x to the negative p dx, so I can just use the power rule. So when we anti-differentiate this, right, we add 1 to the exponent, and then we just divide by that exponent. We evaluate this from 1 to b. And so just to make this look a little nicer, I'm going to factor the constant out front, but negative p plus 1 looks kind of gross. So I'm going to write that as 1 over p, or excuse me, 1 over 1 minus p, right? I just wrote it in the opposite order so we can see that it's still 1 plus negative p. Then I'm going to move this guy into the denominator, and when I move it into the denominator, I have to multiply the exponent by negative 1, right? Because that's what we do. We change the sign. So now this becomes p minus 1. Because negative p becomes positive p, 1 becomes negative 1, right? And we're going to evaluate this still from 1 to b. So p is a constant, so I'm just going to factor that out front, and we're going to get 1 over b to the p minus 1 minus 1 over 1 to the p minus 1. So this is what I need to take the limit of as b goes to infinity. Now this second term right here, I can just write it as 1 because 1 raised to anything is going to be 1, right? So this is just going to be minus 1. So now what I have to do is evaluate this limit, but this is where I got to break p up into a couple of cases, okay? So the first condition is, well, what if p, is between 0 and 1? What does the limit look like? So if the value of P is between 0 and 1, so let's just pretend for a second it's 1/2, okay? Well, if you look at that denominator and that exponent, 1/2 minus 1 is negative 1/2. So that negative 1/2 would put the B back up in the numerator, and you would get B to the positive 1/2. What's the limit of the square root of B as B goes to infinity? Infinity. So 1 over 1 minus P times the limit as B goes to infinity of 1 over P equals infinity, and this thing diverges. So, oops. So just later, just think about it, let P be 1/2 and see what happens, right? If you actually plug in a real number, you'll see it jumps back to the numerator and you get infinity, all right? If P is greater than 1, so if P is greater than 1, we can pick any number bigger than 1 we want, so let's just pick 2, right? Well, then you get the limit of 1 over B, right? And what's the limit of 1 over B as B goes to infinity? 0, right? So we get 0 minus 1, right? Still times 1 over 1 minus P. And it's okay that it's negative. It's an actual constant real number, so the limit exists. So these converge. If P equals 1, well, we can't jump straight to the limit, because if P equals 1, we would get a different result out of our integral. So if P equals 1, then the integral from 1 to infinity of 1 over x dx is ln of x from 1 to b, right? ln of 1 is 0, so all you have to do is look at the limit of the natural log of b, and we get infinity, so it diverges. So remember, integrating with P equals 1 in the denominator would actually produce a different result out of the limit. So what we can see here, right, in conclusion, they're always going to diverge if P is greater than 0 up to being equal to 1. They converge when P is greater than 1. So even if you see 1 over the square root of n, that's a P series where P is 1/2. If you had, 1 over n to the 3/2, that's a P series where P is 3/2, and that's greater than 1, so that would converge, okay? So even with radicals, sometimes if we can always write it as a power, we just simply have to apply, is P between 0 and 1, or is P greater than 1, okay? So like I said, on the exam, I might say, prove to me that 1 over n to the 5th converges, right? Or I might say, prove to me that 1 over n to the 1/2 diverges. And you would show that to me by actually just doing the integral test, but you'd actually have a number, and you could just integrate it out, take the limit, and then show me whether you get converging or diverging. But that's how you prove a P series converges or diverges, by doing the integral test. Right? Now this also makes sense from what we said earlier, is that as the value of P gets bigger and bigger, those denominated, the 1 over that, right, that's going to 0 faster and faster and faster. So if you test around 1, we see the tipping point, right? When it's at 1, it diverges, but as soon as you get beyond 1, it gets to 0 fast enough that it converges. Any questions on that? All right, so let's look at some examples, and then we'll take our quiz. And the quiz will be over, remember, 9-2, not this. We'll do a quiz over this next Tuesday. So I don't like to do quizzes on Mondays in here. We just don't have enough time. So this is a really straightforward one. You should be like, that's a p-series. And here's how you would show. You can simply say, it converges because it's a p-series where p equals 2. That's all you have to do. One over n, right? We would say it diverges because it's a p-series and p equals 1. Huh? You could also say it's a harmonic series. Yep. So if I gave you something like this, well, we would rewrite it. I do want to see you at least do this next step. I do want to see you change it into the form of a p-series. And then you can say it converges because it's a p-series where p equals 3. So this series is going to start from 2 and go to infinity. And this goes back to your earlier question. What would be an example of something that looks like a p-series but is not actually a p-series? Okay, and that's because that natural log is in the denominator. So we can't simply say this is a p-series where n equals 1, or this is a harmonic series. So this is actually something we can integrate. It is reducing, it is continuous, it is positive, so we would have to apply the integral test to show that this is, whether this is converging or diverging. So we would compare this, we're integrating from 2 to infinity of 1 over x natural log of x, and this is going to require a u substitution, but rather than letting the entire denominator be u, I'm going to let u be the natural log of x because the derivative of the natural log of x is 1 over x. So I can replace ln of x with u, and my 1 over dx, or x dx, would be my du. So this is a very straightforward integral. We just get 1 over u du. That's going to equal the natural log of u. So when we go back to x, that's the natural log of the natural log of x evaluated from 2 to b. And if the limit of the natural log of b goes to infinity, then the limit of the natural log will also go to infinity. And that's because the inside stuff is going to infinity. So then when you take the natural log of b as it goes to infinity, it's still climbing to infinity. So this thing would diverge. All right, so before we start the quiz, I just want to check, because we're done with this section. This is really short and sweet. Does anybody have any questions about any of this? Anything they want to? Yep. I'm sorry? How come we use b instead of n? Because when we're doing improper integrals, it's just sort of convention, right? The standard definition of an integral is the indices are from A to B, right? That's how we define intervals. So usually when the thing we're dealing with that's an issue is at the top, we call it B. And when the thing that we're dealing with is at the bottom, we call it A. And the reason we don't go back to N is because N doesn't have anything to do with this, right? We're looking at the series, and then we're comparing it to a function, and then now we're just integrating the function. So there's no reason to bring N back into the game, because N is the natural counting numbers, right? And this is a continuous function we're looking at. All right, good? Anything else? All right, cool. Oops. So for the first one, these are geometric series, and I need to know if they converge or diverge, and if they converge, you need to calculate the sum. So that means for these two, since I'm giving you the terms out, you're going to actually have to write the series in the form of a geometric series, so then you can see if it's going to converge or diverge and then calculate the sum. All right, the second one. Oh, sorry. This is a minus. This is a minus. So we have a little pattern recognition for the first two. Oops. And make sure you're paying attention to the conditions that have to be met in order to sum. Zoom out a little bit. So everybody got number 1 copied? Okay, I'll do that. How about I just do that? Here we go. I'll have the hard copy for you guys in just a second. I just need to make sure I get it all on camera. So what I mean for 3, when I say give a reason, you can't just write converge, diverge. You have to show some kind of work of how you got there.